Hi everyone, Professor Bob Young here. In this instructional video, we're going to discuss the law of cosines, which are also used to find missing sides and angles of oblique non-right triangles. Now, in our last instructional videos, we discussed the law of sines, so you knew there had to be ones involving other creatures, so that's what we're going to look at right now. Now, the law of sines, you may be given two sides and an included angle here. So you may be given what they call side, angle, side, and we'll look at the formulas here, involve those. And the alternate form is when they give you three sides of an oblique non-right triangle. So they may go ahead and give you all three sides, and then you can find the missing angles on these. All right. Now, if you're interested in the proof for the law of cosines, I put a link down here on the bottom. I did the proof for the law of sines for you in the last videos, but I found a pretty good one. You may get tired of hearing me all the time, so I'll let you look at some other things and give you some suggestions there if you're interested. All right, so we're going to go ahead and apply these formulas here and look at some examples and also do some real life applications of where this would be used. All right, so for example one here, just going into the homework, notice this oblique triangle. It looks like it's a side angle side as we mentioned before. So it says solve the triangle given angle A is 44 degrees, side B is 4, and side C is 8. All right, so I went ahead and I wrote the formula here using one of the SAS formulas based on what I was given here. So I'm saying A square is going to equal B square, which in this case is 4 square, plus C square is going to be 8 square, minus 2 times B is 4 times C is 8, times the cosine of angle A was given as 44 degrees. Now, to solve this for A, remember, the formulas are given as A square, B square, and C square. And notice if you're thinking about the Pythagorean theorem for right triangles, the third one says A square plus B square equals C square, and then it throws on the rest of the end part of it here. So the proof will show you where that comes from. But if you're trying to remember some of these, it's almost like the side that you're after, this side opposite angle A, you have to use these two sides in unison first, and then that angle that you're given. All right, so when we get to the application problems, I think that'll become more apparent. So right now, let's go ahead and take the square root of both sides of this. All right, so what I want you to do is go ahead and take out your calculator and give me this answer rounded to the nearest tenth just to make sure we're getting the same answer. And I'll do it on mine and pause real quick here. All right, I got 5.8 rounded to the nearest tenth for A here. So what we're going to do next is go from there. I'll go ahead and write that answer down on my paper here and we will continue. Now, once you get A is 5.8, let me go ahead and put that in here. You can now use the law of sines to finish out these other parts that you're after here, angles B and angle C. So if you remember the law of sines, it is from the last videos, side A over the sine of angle A equals side B over the sine of angle B equals side C over the sine of angle C. Now I also seen some instructors, keep using the law of cosines on this, but using the law of sines from this point is much more advantageous and it'll be a lot quicker for you. All right, so let me go ahead and put in what we know here. So we know we have 5.8 and then over the sine of 44 degrees equals 4 over the sine of angle B, which we will find, equals 8 over the sine of angle C, which we will find. So I think I'll go after angle B next by cross multiplying, setting those equals. So we'll say 5.8 times the sine of angle B equals 4, so this should be review from our previous lessons, times the sine of 44 degrees. Divide both sides by 5.8. Okay, so we'll have the sine of angle B will equal this. So we're going to take the inverse sine, arc sine, or was what Young likes to call the angle getter, and we'll go ahead and take the inverse sine of this. So again, I'm going to pause, let you do it. Now make sure you're in degree mode. If you're in radian mode, you're toast, and we'll come back and it says round this to the nearest degree. All right, I got about 28.62, so I'm going to round that to 29 degrees, and then we will go back, and now we can get the third angle C by taking 180 degrees minus the 29 degrees, which we just rounded, minus A was 44 degrees. And let me go ahead and get that real quick, and we should be done with it. All right, so I ended up with C is 107 there. So what we're going to do next is go ahead and check those three answers in here. All right, so I put those answers in. Let's see how we did. Nice. All right, for example 2, let's look at the given triangle. Now this is a case of side, side, side they're giving. And whenever you're given three sides, always go after the largest angle first. Now in this case, I hope you see that's angle B because it's opposite the largest side. Now you have to be careful on some of these because I've seen some problems where you go to get angle B and they split this triangle out from this part a little bit and you end up getting the triangle that is over, or I'm sorry, the angle that's over here instead of the one you want. And you'll be able to tell when you use the law of sines, you got to make sure that your largest angle's opposite your largest side, smallest angle opposite smallest side, and so forth. So let's go ahead and set this one up. All right, so I went ahead and wrote the cosine formula here using the alternate form side, side, side as the cosine of angle B here. So that's the side, that's the angle that's the largest one we're going to go after. So we're going to go ahead and plug in what they gave us. So the cosine of angle B is going to be 2 squared plus C is 6 squared minus B is 7 squared all over 2 times 2 times 6. All right, now once again, to get to the angle, you have to undo or take the inverse operator of cosine, which again is called the arc cosine, the inverse cosine, depending on your instructor, or the angle getter. So I'm going to let y'all pause, put this in your calculator, and then we will get angle C, or I'm sorry, B. We'll get the other ones too in a second, and then we will round that to the nearest degree. All right, I'm back, and I got about 112.024 degrees, so to the nearest degree, we're going to go ahead and round this to 112 degrees. And just like in the previous examples, we're going to go ahead and use the law of sines now to get the other angles here. So we're going to say that A over the sine of angle A equals side B over the sine of angle B equals C over the sine of angle C. And we'll go ahead and plug in what we know here. So we know the sides here, 2, 7, 6, and we just found the largest angle, the cosine of B here, or I'm sorry, the sine, well, angle B is 112 degrees. I'll spit it out. Okay, using the law of cosines. And notice we have what's called an obtuse oblique triangle here because we have one obtuse angle greater than 90. All right, so we'll go ahead and either you can solve and get angle A or angle C, and once you get one of those, you can subtract from 180 and get the other. So let's go ahead and pause a second. Let's see if you can pause and do that and get those other two angles, and we will continue the adventure. All right, let's see if we ended up getting the same answers together here. So what I went ahead and did is I cross multiplied 2 sine 112 degrees equals 7 sine A, divided both sides by 7. To undo the sine here, I took the inverse sine or arc sine of both sides, put that in my calculator. Well, I've got angle A was about 15.36, which I rounded to 15 degrees. All right, came over. C is then going to be 180 minus the 112 we found initially here, minus the 15 we found, and I got 53 degrees. And I'm going to plug all those in and check them now. And hopefully you're getting the same thing and everything's going well. So make sure you're using those calculators correctly. I don't care what model or brand you have, but you have to work at these and make sure you're getting the correct results. Alrighty, so I plugged the three answers in. Let's see how we did. All right, well done. On to the next example. All right, example 3 and the continuing examples are going to be where the law of cosines is used in real life. So we're going to take some different aspects of what we've learned so far in the course and apply them here. Now on this one, it wants us to go ahead first and find angle C. So this is kind of good final exam review here because they give us a 14-degree angle to the left here and a 35-degree angle to the right. So we should be able to look at this and say that C, since this is a straight line, adds up to 180 degrees. All right, so the first thing we're going to do to get angle C is subtract 35 and 14 from 180. All right, now I went ahead and found that angle C is 131 degrees here. So now we can find side C by using the formula C squared equals A square plus B square minus 2 times A times B times the cosine of C. So we've done an example similar to this. So I'll pause here, let y'all see if you can bring this home, and then we'll check it and move on to even more application problems. All right, so plugging into the formula here, I let A be 13, B be 7, and then of course the angle we found earlier was 131. So when I took the square root of both sides, I ended up with side C is 18.36. It wants us to round it to the nearest tenth of a degree, or the sides, I'm sorry, to the nearest tenth. So I went ahead and made that 18.4. So let's go ahead and check this one real quick. All right, checking them here. 131 looks good, and then let's check the 18.4. So be careful when it says round or to the nearest whole number, nearest tenth, whatever, and I think you should be good. All right, let's head on to some more examples. All right, in this example, we have a application problem involving bearings. So it reads, two ships leave a harbor at the same time. One ship travels on a bearing of south 12 degrees west at 15 miles an hour. The other ship travels on a bearing of north 75 degrees east at 10 miles an hour. How far apart will the ships be after 3 hours? Now, students in my lecture classes know what I want them to do already. I want you to pause this video and I want you to draw a picture of depicting what's happening in this problem. So take a minute, see what you got. We'll come back, compare notes, and see where to go from there. All right, so we're back here. So I went ahead and I made a little compass poo, north, south, east, west, and I said that going in a south 12 degrees west position, this angle here would be 12, north 75 degrees east. So make sure you always use north and south first for your bearings and then travel easterly or westerly directions. All right, so what we need to do is now use, if you remember the old distance formula from your previous classes, distance equals rate times time. So the ship that's going in the southwesterly direction here has traveled 15 miles an hour for 3 hours. So we just have to go ahead and plug that information in here. So this ship has sailed, it's gone 45 miles in the southwesterly direction. The other ship that's going north 75 degrees east would be 10 times 3 or 30 miles. So if you multiply miles per hour by hour, you will get miles here. So this ship at this bearing has traveled 30 miles. All right, now what we need to do is go ahead and get this distance between them here, and that's what we're going to use the law of cosines for. All right, now if you look at this picture, I'm going to give you a minute. I want you to see if you can figure out how to get this angle here in the middle, because this one looks like to me that it's going to be an SAS example. I mean, we definitely have two sides given, but I think we need this angle in the middle here. So pause, see if you can get it, and I'll come back and work with you, and we'll see if you got the correct solution here. All right, did you figure it out? Well, here's what I'm looking at. I know that this bearing was 75 degrees, and these two angles are complementary. They are going to be 90 degrees here when you add them up. So this angle here has to be 15 degrees. This is a right angle in here, and they were kind enough to give us this south 12 degrees west bearing. So the angle we need, this angle across from side X, is going to be 15 degrees plus the right angle 90 plus 12 degrees. All right, now you have all your formulas and everything, but this is what I mean about knowing how to apply the formula. All right, now you could label this triangle as angles ABC, sides ABC, but what I want you to start getting a feel for is this. If you take this opposite side, which we're after X, and square it, those two sides, how the formula is going to work is going to be X squared is going to equal 45 square plus 30 square minus 2 times 45 times 30 times the cosine of that 117 degrees. So we can actually find the distance those ships are apart by using our SAS formula. Now again, if you take the square root of both sides to solve here, and that's going to be, I ran out of writing tablet on that one, a long square root there. X is going to be, and notice it says round to the nearest tenth. We will find the distance quickly here. So I'll pause and let y'all do that. All right, did you get 64.426? And I had to round that to 64.4 miles. Let's go ahead and check it. And nice. All right, for our next application problem, it says the figure to the left shows a 500-foot tower on the side of a hill that forms a 6-degree angle with the horizontal. Find the length of the two guy wires that are anchored 60 feet uphill and downhill from the tower's base and extend to the top of the tower here. So let's go ahead and label some things we know in this problem and see if we can reason out some things. All right, now we know the tower's height is 500, so I'm just going to go ahead and I'm going to put that length in here, the Tower of Terror, so they say. And then we're also notice that this is at an angle of 6 degrees, so one of these angles must be obtuse and the other one must be acute. So I'm hoping you see that if this is 6 degrees in here, I wish I could blow that picture up a little bit more. I could, but then you might not see it. Then this would be 6 degrees here if this were going to be level. So I think this is going to be what we're going to call 96 degrees, this angle. And then we'll subtract 6 from 90 here. This looks like the acute one here. And if you want to, you can kind of blow that up. And I think you'll see that this is the relationship. All right, so we'll go ahead and call this guy wire x and this guy y are y, and we'll go ahead and plug in and use our law of cosines to determine this one. So what I'm going to say here is x squared equals 500 squared plus 60 square. So notice this is another example of side angle side. They gave us the height of the tower and they gave us the distance 60 feet apart from the both ends there. So I'm going to say x squared equals 500 square plus 60 square minus 2 times 500 times 60 times the cosine of what? Y'all tell me. This is why I'm saying you have to not just know the formulas, but how to apply them. So if we're after x, I think we're looking at the 96-degree angle there. And then we're going to go ahead and do the same thing to get the other length of the guy y, or y square would also be 500 square plus 60 square. So when you do one of these, just, keep it in your calculator and you'll be able to knock both of them out pretty quick. Times 60 times the cosine of the y guy wire would be 84 degrees. So go ahead, stop, pause there, and see if you get these two answers. It'll give you good practice using your calculator, and I'll come back and we'll check them. All right, so I'm back. I've got the X guy wire as 509.8 feet, rounded to the nearest tenth as the problem indicates, and the Y guy wire as 497.3 feet. So we'll go ahead and check that in the answers next. Now, even though you get to this point, you have to be kind of careful on where to put what answer where. It says, what is the length of the uphill guy wire? So I'm thinking that that's the one that's higher up the hill here. So I'm putting the Y one, 497.3. And then the downhill guy wire, the longer one, should get the 509.8. Bang. All right, in our next example, we are going to discuss parallelograms and all the different facets that they entail. So it says in this problem, the lengths of the diagonals of a parallelogram are AC equals 22 centimeters and BD equals 26 centimeters. The diagonals intersect at an angle of 35 degrees. Find the lengths of the parallelogram side, and it gives you a hint here. It says diagonals of a parallelogram bisect one another. Now there are a lot of things going on with a parallelogram, so let's go ahead, stop, pause, and draw this figure here. All right, I'm back. Now I've drawn the parallelogram ABCD here. Now, what the hint was is that these angles, and I don't know if you remember your old high school geometry class, but these angles inside here are called vertical angles. Vertical angles are congruent, so we're going to go ahead and label this angle and this angle the same as would these two angles would be the same. All right, now they also tell us the diagonals AC and BD, they give us the lengths of those, but they also, on a parallelogram, when the diagonals intersect here, they bisect. So in other words, if AC is 22, we know that this length is 11 and this length is 11, so it'd be half of 22. And then BD 26, we would get 13 and 13 here. All right, now it says the diagonals intersect at an angle of 35 degrees. So I'm thinking that which one of these angles looks more like 35 degrees if we drew this right. I'm thinking that this would be 35 degrees, as would this. 35 degrees. And then what would these other two angles be? Now again, here's good exam review. We've got a straight angle here, so these two would be supplementary. So 180 from 35 here would give us these other two angles in the middle, and then we can find what we're after. All right, so I went ahead and said that's 145 degrees, subtracting 180 from 35. So let's go over here now, and if we want to find, let's go ahead and get side AB first. And here again, notice the formulas here. I'm going to say that that length squared is going to equal, so I'm going to look at this top triangle here. And I'm going to say to get that, it's going to be 11 square plus 13 square minus 2 times 11 times 13 times the cosine of 145 degrees. And BC squared. All right, so if I wanted to get this side, now remember AB is congruent to CD and AD is congruent to BC. So once you have those, you'll have it. So we can look at this one here and it would be very similar. It would be 11 square plus 13 square minus 2 times 11 times 13 times the cosine of 35 degrees. So take the square root of both sides on this one, and I think you'll have those answers as well. So I'll go ahead and let you finish that one. All right, so I have the length of AB is 22.9 rounded to the nearest tenth, and BC is 7.5, which we'll go ahead and plug in and check here. And it looks like that got the job done. All right, now for our last example, this is a derivation of the law of cosines, and this is a famous Greek mathematician named Heron who came up with a area formula for any oblique triangle. And here's what his formula says. The area of any oblique triangle, and notice he's labeled the sides A, B, C here, equals the square root of S times S minus A times S minus B times S minus C, where S is the sum of the three sides divided by 2. Now, a lot of students will miss this on the test or in assignments because they'll try to divide by 3, but this brilliant mathematician here came up with this formula, so we're going to go ahead and apply it to our last example here. So it says find the area of the triangle specified below. So it gives us side A is 25, B is 13, and C is 24. So let's apply the famous Heron's formula. All right, so the most important part of getting the area of this triangle is to make sure you get this S number correct. So I took the three numbers, added them up, divided by 2, and I got 31. So what Heron found out, and I'm going to make a giant square root here, is if you take the square root of that S number times that number, subtract every side, and multiply them together here, that you will find the area, in this case it's going to be in square meters, of that triangle. All right, so let's go ahead and put this in our calculator. A lot of students will start saying, put one of these on the test, Young, put one of these. They're nice, and I just might do that for y'all here. So let me pause and we'll get this answer and we'll be done with this section. All right, I'm back. So I took the square root of 31 times 31 minus 25 times 31 minus 13 minus 31 minus 24. I got about 153.09, which I guess we can go ahead and plug in, round it to 153. And that concludes our lesson, Law of Cosines. B. Young signing out.